Hello, my name is Roberto Parra, and I am presenting my solution for the Embedded Engineer Take-Home Test. The core challenge of this project was to design a reliable bridge between a modern, high-level client API and a low-level hardware interface that simulates real-world stability, such as freezes and timeouts. To solve this, I designed a microservices architecture composed of two specialized components: the controller built with Fast API and Python, and the driver built with C++. To start, I'll start by deploying the Docker containers on the server via SSH. So I am rebuilding the containers to ensure we are running the latest versions of them. And as we can see, the Docker build process has finished. Now that the containers are running, we will make the demo. Here I have arranged the logs to follow the data flow. On the left we have the controller, at the center we have the C++ driver, and on the right we have the hardware simulator. And here at the top I have Swagger UI. Let's perform a health check through a ping command. So we have received a pong and a message that the system is online and responsive. We can see in the hardware that the ping command arrived and the driver processed it back to the controller. Since now we know that the system is stable, I am going to issue a reset command. And as we can see, the driver and the hardware simulator process the reset command, and we get a message here that the system reset has completed successfully. Now, since we requested for a reset of the system, we know we are at the idle state, so let's get the state from here. And as we can see, the operation was successful and the current state is idle. So now let's test the set state command. Since we are in idle, we can only change to config state, but I am going to send anything else. As we can see, we have an unknown target state because I have a typo here. So if we execute the right command, we see that we have successfully changed from idle to config. So from here at the config state, let's try to get into capturing mode, and that is forbidden. Here we have a conflict, and the response was this operation is forbidden in the current state. Okay, so let's transition to the idle state. So here in idle state, I am not able to go to the capturing state because of the business rules. We have the message that this operation is forbidden in the current state. Okay, since we are again in the idle state, let's try something else. Let's try to trigger an image capture. So we have triggered a frame capture, and a couple of seconds later I will get the frame by issuing a getFrame command. So okay, the data flow is seen here, and we even stored the hex file with the frame data in the server. So now let's trigger a frame capture and quickly request the frame. Here we have that the capture is still in progress, so we have to wait a moment and try again. And a couple seconds later, let's execute the getFrame command again. And we have another hex file for this particular frame. Now, since we have gotten frames, now we are in the idle state. So let's try to get a configuration parameter. For example, gain. And since we are in the idle state, we are not able to get any config. So we must switch to the config state. Now we can see we are in the config state. Now we can get the config parameters. For example, in this case, the gain is set to +5. So I have set the left pattern parameter to have a value of A, and this is because I need to test that we are able to switch to the photometric mode. So here we have the photometric mode enabled. Here we can see the response, and let's try to change the left pattern and switch it from A to C, for example. And as we can see here in the driver, we have a logic dependency violation. So this command is not arriving into the hardware, and we have a response in the controller. Logic violation, the driver blocked this operation. Now, since we were able to get config parameters, let's set one. For example, the gain with $N and a valid value. Let's execute this. And we have an unknown parameter name. So now we switch to the right parameter, but with an invalid value. And here it says validation failed because it is out of range for this particular parameter. So if we send a valid gain, the command is complete. The gain set to +0. So now let's try the opposite. Let's switch to photometric mode off. So okay, we have switched to photometric mode off, and let's switch the left pattern to another value such as D, for example. So okay, the left pattern was set, and then let's try to get into photometric mode again, and this should be rejective. So okay, here at the driver we have a dependency violation again. This is forbidden because we can't enable photometric mode if we don't have an A let pattern. So now let's test bonus feature, and is the statistics gathering. So if we execute this stats command, we get this response that has commands. Every single command we have called, with the number of calls, the errors they have, some latency statistics, the average, the mean, and the max for each command. And if we need to reset these stats, we can issue this delete stats command, and all metrics have been reset manually, as we can see here. And if we execute the stats get, the command's object is now empty. So when I was showing you the getFrame command, I told you those frames were stored here in a separate folder inside the controller container. And we can see the contents of many frames I have requested. Hey guys, just a couple final thoughts here. I really enjoyed this project, specifically designing the driver to absorb the hardware instability so that the controller remains clean and focused purely on a logic. It was a very satisfying problem to solve. The full source code is in the repository, and I would love to walk through the implementation if you want. Thank you very much for your time.